I was thinking about this earlier. There is this, I don't know, this profound cognitive dissonance in how we actually interact with modern computing right now.
Oh, absolutely. It's totally disconnected from reality.
Right. Like when you pull out your phone and type a prompt into an AI or you ask it to generate an image or whatever, there is this illusion of total weightlessness.
Yeah, you just hit enter and wait for the magic.
Exactly. You hit enter, you get that little minimalist loading animation spinning for a second or two, and boom, the answer just appears.
Yeah.
It feels like pure abstraction.
It really does. It feels like you're just communicating with this, I don't know, digital brain floating somewhere in the ether.
But if you were to actually trace that request, right? Like if you could follow that fiber optic signal from your phone all the way down to its final destination, you wouldn't find a floating brain. You wouldn't find a cloud at all, actually.
No, far from it. Not even close. You would find a physical reality that resembles, like, a heavy industrial manufacturing plant way more than it does any sort of ethereal cloud.
Right. You'd find this massive, incredibly loud, blisteringly hot factory of heavy iron. I mean, we are talking about row after row of reinforced steel racks.
Yeah, and massive power conduits, like cables thicker than your arm.
Thicker than your arm, and thousands upon thousands of these highly specialized computer chips pulling down enough electricity to, well, literally power a mid-sized city.
It's wild. It is a incredibly dense, heavy, and thermochemically volatile reality.
Thermochemically volatile is the perfect way to put it. And that physical reality forces this massive engineering question, which is, how do you actually orchestrate all of that?
Right, because you can't just plug 10,000 cutting-edge AI chips into a wall, throw a switch, and expect them to magically coordinate into a seamless multi-tenant cloud service.
Yeah, the hardware is just the raw ore. You have to have a highly specialized operating system just to manage the factory itself.
And orchestrating that factory has very rapidly become one of the most complex logistical and software engineering challenges of our entire time.
Well, without a doubt.
The hardware, the silicon that gets all the press and the magazine covers is really only half the story. The invisible layer, the software infrastructure that actually marshals that hardware into usability, that's the actual bottleneck for the future of artificial intelligence.
Which perfectly brings us to our mission for today's deep dive. We are looking at a single, incredibly dense source today.
Yeah, it's a heavy one.
It really is. It's just a 4-page software datasheet, but it's dense. Specifically, this is version 2.1.1, copyright 2025,
Right.
from Supermicrocomputer, Inc.
Right.
And it outlines the architecture of what they call their SuperCloud Software Suite.
It's a genuinely fascinating document because, data sheets like this are usually just dry lists of technical specifications,
Yeah, just endless part numbers and SKUs.
Exactly. STU's designed strictly for procurement officers. But if you read between the lines here and you understand the technical hurdles that you're trying to clear, this document is essentially a blueprint for how to build, cool, and monetize a hyperscale AI data center.
Yeah, it is quite literally the operating system for an AI factory.
Precisely.
Well, that is exactly what we are going to do today. We're going to deconstruct this datasheet layer by layer. We are going to figure out how these companies take raw, blistering computing power and turn it into the usable, self-service AI tools that, you interact with every day.
And how they do it all without the entire system melting down into a puddle of expensive slag.
Right. Or just becoming an absolute logistical nightmare for the site reliability engineers. So, okay, let's unpack this starting with the macro view.
Yeah, so the datasheet leads with a very deliberate positioning statement right at the top. It defines the SuperCloud Software Suite as an intelligent software for DCBBS AI infrastructure management.
The DCBBS.
Right, and it specifically highlights that it is tailored for next-generation AI neocloud and enterprise service providers.
So right out of the gate, let's look at that terminology. DCBBS, Data Center Building Block Solutions.
Yeah, it's a bit of a mouthful.
It is, but it speaks to a very specific architectural philosophy, doesn't it?
Yeah.
You aren't bespoke wiring every single server like the old days.
No, not at all.
You are designing these massive, repeatable blocks of compute, storage, and networking. Blocks that can just be stamped out and scaled horizontally as you grow.
Exactly. It's modular hyperscaling.
Right. But the term that I really want to drill into here is neocloud. Because this datasheet isn't targeting AWS or Azure's legacy infrastructure.
Yeah.
This is something else entirely.
No, neocloud is a critical market distinction right now because if you think about it, For the past decade, the traditional cloud is built entirely around generalized workloads.
Yeah, hosting websites and stuff.
Right. You've got massive data centers optimized to host thousands of individual web servers, traditional relational databases, standard virtual machines. But the demands of modern generative AI are fundamentally different.
They break the old model.
They really do. Traditional cloud architecture actually buckles under the pressure of AI training.
And that's largely because of the east-west traffic. Right?
Yes, exactly.
Because traditional clouds are built for north-south traffic. A user on the internet requests data from the server, that's south, and the server sends it back out north. It's vertical.
That's a great way to visualize it.
But training an AI requires thousands of GPUs to talk to each other constantly, right? They're sharing massive data sets across the internal network, moving laterally east-west.
Right. The synchronization requirements are just staggering. If you have, say, 10,000 GPUs training a single massive language model, and the network between them stutters for even a fraction of a millisecond,
It hangs.
the entire cluster has to pause and wait. All 10,000 chips just sit idle, waiting for that one dropped packet.
Wow.
So a neocloud is this entirely new breed of cloud provider built from the bare metal up exclusively for synchronous high-performance computing. They strip out all the legacy virtualization layers that add latency.
And the datasheet confirms exactly that. It says this suite spans from provisioning to managing to maintaining, enabling self-service, multi-tenant AI clouds. And the service catalog they list is really telling. They've got bare metal as a service, virtual machine as a service, GPU as a service, and AI model as a service.
It's all about direct access.
Right. They are offering pure, unadulterated access to the hardware for customers who literally need to bypass the hypervisor completely just to squeeze out every single drop of performance.
And that level of raw access introduces immense complexity for the provider. Because when you offer bare metal or GPU as a service, you are basically handing a customer the keys to an incredibly powerful, incredibly expensive machine.
Like a multi-million-dollar Ferrari.
Exactly. And you need a management plane that can instantly wipe that machine, totally reconfigure its network topology, and hand it to the next customer securely, the very second the first customer's lease is up.
Man, it makes me think of like an automated hyperscale logistics port. If the GPUs are these massive cargo ships capable of hauling unprecedented amounts of freight, this SuperCloud suite isn't the captain of the ship.
No.
It's the automated crane system, it's the rail yard router, the customs clearinghouse checking security, and the harbor master directing traffic all functioning autonomously at light speed.
That's a really good analogy. And if we connect this to the bigger picture of the AI gold rush, that orchestration layer is where the battle is actually won or lost.
How so?
Well, the datasheet explicitly hammers on the need for the fastest time to online. When a neocloud provider buys a cluster of high-end GPUs, the capital expenditure is just astronomical.
We're talking hundreds of millions.
Right. So every single minute those chips are sitting idle while, IT manually configures the network or updates the firmware is burned revenue. They require hyper-specialized automation just to get those engines running and ingesting workloads instantly.
Which brings us to the foundation layer. Because before you can lease out a GPU cluster to an AI startup, you have to actually wake the bare metal up, introduce it to the network, and prove that it works.
Yeah, it doesn't just work out of the box.
Exactly. And this is handled by the very first component listed in the suite, the SuperCloud Automation Center, or SCAKE.
SKC, right. This is where we drop down to the absolute silicon level. The datasheet defines SCAKE as a scalable workflow engine.
Okay.
It's designed to extend automation by deeply integrating with tools that infrastructure engineers already use, things like Ansible playbooks, shell scripts, and Kubernetes operators.
Right, the industry standard.
Exactly. And it uses them to enable self-service runbook automation.
Yeah, and it lists a massive scope for these automated runbooks, like reading through it. It handles OS provisioning, deploying Kubernetes and OpenShift clusters, configuring Slurm for workload scheduling.
Huge for HPC.
Yeah, HPC, high-performance computing. And it's also installing its own SuperCloud components, running massive firmware updates and conducting DPU benchmarking from the core data center all the way out to edge deployments.
The scope is massive because the blast radius for manual error at this scale is just catastrophic.
Give me an example.
Okay, let's look at firmware updates, for instance. In a heterogeneous AI cluster, you don't just have one type of server. You have different generations of motherboards, various network interface cards, different storage controllers.
And, of course, the GPUs themselves.
Right, dozens of variations. And each of these components has its own low-level firmware.
And if the firmware on, say, the network card in rack 12 doesn't perfectly match the expected protocol of the switch it's plugged into.
You get packet drops. And suddenly, your multi-million-dollar training run is crippled.
Because of one mismatch.
Exactly. So coordinating a rolling firmware update across 5,000 interconnected nodes without causing a cluster-wide outage is a logistical nightmare.
I can't even imagine.
So SCAC essentially orchestrates this deployment. It ensures dependency checks are met, it executes the updates in parallel where it's safe, and it automatically rolls back if an anomaly is detected.
Okay, that makes sense. And the GPU benchmarking phase caught my eye immediately, too. Because you don't just rack $1 million worth of hardware and assume it's going to hit its theoretical teraflop limits out of the box.
Never. Silicon lottery is a real thing.
Right, so the Automation Center actively stress tests the silicon. It forces the GPUs to run localized matrix multiplications to ensure they aren't thermal throttling or throwing memory errors before they are ever placed into the available inventory pool.
Yeah, you have to prove they work under load. And the business outcome of automating all of this is pretty stark. The datasheet cites a 30 to 50% reduction in repetitive manual work.
That's a massive OpEx saving.
Huge. In an industry where highly skilled infrastructure engineers are incredibly scarce and super expensive, you simply cannot afford to have them manually SS etching into servers to execute command line updates. SCE abstracts all that toil.
But freeing up engineering time isn't even the most critical outcome listed here, which is wild.
No, it's not.
The datasheet emphasizes that SCAC ensures risk assurance through integrated AAA, RBAC, and secrets management. Now, I understand the basic principles of zero-trust architecture, but how are they applying these mechanisms specifically to a bare metal AI factory?
It's a great question.
Because a compromised runbook here doesn't just mean a data leak. It means someone has root access to a literal supercomputer.
That threat model is exactly why this is so tightly integrated. Let's break down the implementation. AAA, authentication, authorization, and accounting is the bedrock here.
Okay, walk me through it.
So in a hyperscale environment, authentication isn't just a username and password. It's often tied to biometric hardware tokens or federated identity providers.
Sure, multi-factor on steroids.
Right. But the authorization and accounting parts are where it gets really complex.
Right, because if I'm a junior network tech, I might be authorized to view the telemetry data of a switch, but I absolutely should not be authorized to execute a bare metal wipe of a storage array.
Exactly. And that's where RBAC role-based access control plugs in. The SCA engine enforces these roles directly at the API level, and the accounting aspect ensures a cryptographic audit log is generated for every single API call.
So there's a permanent record.
Always. If a command is issued to change a network route, the system logs the exact identity, the timestamp, and the parameters of that command.
Okay, but what about the secrets management? Because you can't just hard code API keys or database credentials into these automated Ansible playbooks, right? That's a massive vulnerability.
Oh, you absolutely cannot. In modern infrastructure, secrets need to be dynamic and ephemeral.
Ephemeral, meaning they expire.
Yes. When a SAC workflow needs to configure a database, it doesn't look up a static password. It requests a temporary, tightly scoped credential from a secure vault. It uses that credential to do the job, and then the credential immediately expires.
Oh, wow. So even if an attacker intercepts it.
If they intercept that token, it's totally useless to them seconds later.
Wow. Okay, so as these take, it's the raw iron powered on, it's updated, it's benchmarked, and it's cryptographically secured. The digital foundation is officially laid.
The factory is built.
The factory is built. But the moment you start actually running those benchmarks, right? The moment those thousands of GPUs start pulling maximum wattage, the digital world crashes violently into the physical laws of thermodynamics.
It absolutely does. Heat becomes the ultimate enemy.
And that forces us to the second pillar of the datasheet, SuperCloud Composer for DCBBS or SCC.
Right. This is where we leave the realm of code and enter the realm of fluid dynamics.
Fluid dynamics.
Yeah. SCC is defined as an all-in-one platform providing a unified dashboard to manage both rack-scale infrastructure and liquid cooling hardware.
Now here's where it gets really interesting to me. I want to focus on this. Because pouring liquid directly through a rack containing millions of dollars of incredibly sensitive electronics sounds inherently terrifying.
It sounds like a disaster waiting to happen.
Right. If one seal breaks, if one fitting is slightly misaligned, it's a catastrophic short circuit. Why on earth are we taking on the massive physical risk of plumbing water into a supercomputer?
It is entirely dictated by thermal design power, or TDP. We have literally hit a physical wall with air cooling.
Really? Air just doesn't work anymore.
It doesn't. In a traditional data center, you use massive CRAC units, computer room air conditioning, to blast freezing cold air under a raised floor and push it up through the server racks.
Right, standard AC.
And that methodology works perfectly fine when a single server rack is drawing, say, 10, maybe 15 kilowatts of power.
But modern AI racks are wildly outside that paradigm. A single rack, densely packed with next-generation GPUs, can draw upwards of 100, sometimes 120 kilowatts.
Yes, and air simply lacks the thermal density to capture and move that much heat. If you tried to air-cool a 120 kilowatt rack, the fans would have to spin at supersonic speeds.
You're kidding.
I'm not. The acoustic vibration alone from the fans would physically destroy the spinning hard drives in the facility.
Oh, wow. The noise would shake them apart.
Exactly. And even with all that air, the GPUs would still thermally throttle and cook themselves within minutes. Liquid, specifically engineered coolants or chemically treated water, has a heat capacity vastly superior to air.
So you pump the liquid directly to cold plates, physically mounted right on top of the silicon dies to absorb that massive heat load instantly.
Right on the chip, yes.
But that brings us back to the risk of leaks. The datasheet explicitly states that SCC manages the PDUs, the power distribution units, and the CDUs, the cooling distribution units. It acts as the central nervous system for the physical plant, providing advanced leak detection and protection to safeguard the infrastructure.
And you have to understand the granularity of that telemetry. A leak detection system at this scale isn't just a moisture sensor sitting on the floor waiting for a puddle to form.
Right, that would be way too late.
Exactly. SCC is monitoring the micro fluctuations in fluid pressure within the cooling loops. It's monitoring the intake and outtake temperatures at the cold plates themselves.
Okay, so if the pressure drops slightly in, say loop 4B, or if the outtake temperature suddenly spikes without a corresponding increase in computational load, the software knows there is a fluid dynamic anomaly before a single trough of water ever hits a motherboard.
Exactly. It's predictive. And SCC's role is to act on that telemetry instantly.
What does it do?
Well, if it detects a critical anomaly, it can interface with the PDUs to instantly drop the power to that specific rack, preventing a thermal runaway, and simultaneously, it commands the CDU valves to isolate and bypass that specific cooling loop.
All automatically.
All in a fraction of a second. No human operator could ever react fast enough to save the hardware.
It's automated disaster prevention operating at millisecond latency. That's wild. And the scale they are claiming here is just staggering. The text boasts that SuperCloud Composer provides observability and tuning at scale, managing over 20,000 hosts through a single unified portal.
Yeah, taking telemetry from 20,000 AI hosts, plus all their associated power and cooling infrastructure, means ingesting millions of highly volatile data points every single second.
Millions per second.
Yes. Consolidating that absolute fire hose of data into a single pane of glass and using it to dynamically tune power consumption to optimize operating expenses, or OPEX. It's a monumental feat of systems engineering.
So let's step back and look at the factory we've built so far. We have SK, which automated the bare metal provisioning and locked it down.
Yep.
We have SEC, which is monitoring the fluid dynamics and ensuring the hardware doesn't literally melt itself into the floor. The physical plant is operational and stable.
Sure.
But an operational factory that only serves one customer at a time is an economic failure.
Usually, yes.
Right. A neocloud provider needs to lease this hardware out to dozens of different AI companies simultaneously to make a profit. So how do you carve up a supercomputer securely? This brings us to component number 3, SuperCloud Director, or SCD.
SCD. This is the traffic cop in the isolation layer. The datasheet defines SCD as a platform delivering multi-tenant AI cloud control, integrating bare metal compute, Ethernet and InfiniBand networking, and multiple storage platforms.
I want to dig into the multi-tenancy aspect here, because achieving multi-tenancy on bare metal is vastly more difficult than in a traditional cloud, isn't it?
Oh, it's night and day.
Because in a normal cloud, you just spin up virtual machines. The hypervisor creates a neat software-defined box for tenant A and another box for tenant B, and they literally never interact.
Right, it's fully abstracted.
But AI workloads often require bypassing that hypervisor entirely for performance. So how do you isolate tenant A from tenant B when they're running on the raw bare iron?
You have to push the isolation all the way down to the network and hardware level itself. This involves heavily utilizing technologies like SRIOV single root I/O virtualization and complex VLAN or VXLAN tagging at the literal switch level.
Okay.
SCD acts as the orchestrator for all of this. So if an AI startup leases 20 bare metal GPUs, SCD communicates directly with the physical switches to create an impenetrable software-defined network perimeter around those specific nodes.
And the datasheet is very specific about the types of networks it manages. It highlights both Ethernet and InfiniBand. Now, managing Ethernet is standard, but integrating InfiniBand orchestration natively, that's what truly marks this as an AI-specific tool, right?
Absolutely. Ethernet is great for the north-south traffic, the developers pushing their code into the cluster from their laptops, but InfiniBand is the circulatory system for the AI models themselves.
Right, for the east-west traffic we talked about.
Exactly. It is a highly specialized networking protocol designed specifically for massive parallel computing. It offers staggering throughput and incredibly low latency, often bypassing the CPU entirely to allow GPUs to write directly to each other's memory.
Remote direct memory access, right? RDMA.
Exactly, RDMA. But configuring an InfiniBand topology, which is usually this complex fat tree or spine and leaf architecture, is incredibly unforgiving.
I've heard it's a nightmare.
It is. If SCD didn't natively understand and orchestrate the InfiniBand subnets during the tenant provisioning process, the whole multi-tenancy model would just collapse.
And they are very aggressive about this positioning in the text. It explicitly states, unlike generic cloud management tools, SCD is built for GPOA, AI factory deployments, and hyperscale operations.
Yeah, that's a direct shot.
It really is. They're basically taking a direct shot at legacy cloud software, saying, do not bring your standard enterprise web hosting tools into this environment. They do not understand the physical topology required to make these chips actually perform.
And that physical awareness translates directly to the bottom line for the providers. The primary business outcome highlighted for SCD is a staggering up to 40% faster time to online.
40%.
Yeah, that means 40% faster tenant onboarding, which accelerates AI model delivery and, crucially, accelerates revenue generation.
But wait, if we are prioritizing raw speed to revenue like automating the provisioning of bare metal servers and configuring complex InfiniBand networks instantly, doesn't that inherently compromise the security audits we talked about earlier?
Usually, yes.
Because moving fast usually breaks things. And in infrastructure, breaking things means creating vulnerabilities.
That is the traditional trade-off, definitely. But SCD attempts to solve that by making the compliance artifacts a direct byproduct of the automation itself.
What do you mean?
Well, the outcomes section specifically notes that it provides unified authentication, role-scoped policies, and complete audit trails for every infrastructure action. This aids regulated industries to deliver GPU servers as a service.
Okay, that makes total sense. Because if a massive financial institution or, a healthcare provider wants to leverage a neocloud to train a diagnostic AI on proprietary patient records, they are governed by strict HIPAA or SEC regulations.
Exactly.
They can't just trust that the multi-tenancy works. They need proof.
They need cryptographic proof.
Yeah.
If they're audited, they have to produce a flawless chain of custody showing exactly how their bare metal environment was isolated, exactly who had access to the underlying management APIs, and exactly when the environment was wiped.
And SCD just does that.
SCD automatically generates that complete audit trail as part of the rapid provisioning process. So it bridges the gap between raw compute speed and strict corporate governance.
That's incredibly smart. Okay, so we have ascended from the bare metal up through the liquid cooling loops and into the secure multi-tenant network orchestration layer.
We're almost to the top.
We are. We have a fully functional, highly secure, rapidly provisioned AI cloud. But all of this infrastructure is utterly useless if the people who actually build the AI can't interface with it.
Exactly, the human element.
Right. We finally reached the human being, the fourth component of the suite, the SuperCloud Developer Console, or SDX.
SDX. This is where the massive complexity we've discussed for the last half hour is finally abstracted away into actual usability.
Thank goodness.
Yeah. SDX is positioned as a developer-first AI experience console. It basically aggregates PyTorch, Jupyter notebooks, containers, AI models, virtual machines, and data services into a single unified workspace, all built on top of standard Kubernetes.
We really have to talk about the friction this solves, because the cultural divide between infrastructure engineers and data scientists is famously massive.
Oh, it's legendary.
Right. The person who understands the fluid dynamics of a CDU and the subnet masking of an InfiniBand network is almost never the same person who is writing Python code to fine-tune a large language model.
No, they speak completely different languages.
The data scientist just wants a Jupyter notebook connected to a GPU. They don't care how the water is pumped.
And historically, that divide caused immense delays. A data scientist would have to file an IT ticket requesting a specific environment with specific versions of CUDA drivers, PyTorch libraries, network access, the whole 9 yards.
And wait for weeks.
Yeah, the infrastructure team would manually piece it together over a week or two. But the datasheet explicitly calls this out, noting that unlike infrastructure-only consoles, SDX delivers turnkey developer agility with self-service provisioning.
So the workflow changes. The data scientist logs into a web portal, they select a PyTorch template, request 4 GPUs, and just click launch.
That's it.
And SDX translates that request into Kubernetes manifests, talks to the lower-level systems to provision the resources, pulls the correct container images, and hands the developer a URL to their workspace in minutes. It completely removes the IT bottleneck.
And the resulting velocity is highly measurable. The text claims SDX enables AI developer velocity, reducing the time to model experimentation and tuning by up to 60%.
That's a game changer.
It really is. When your data science team, which, let's be real, is likely the most expensive talent in your entire company, spends 60% less time wrestling with driver incompatibilities and container orchestration, and 60% more time actually refining the algorithms, that is a compounding competitive advantage.
But the feature in SDX that truly blew my mind is the mechanism they use to achieve this efficiency at the hardware level.
Oh, the slicer.
Yes, under the technical capabilities, it highlights intelligent GPU slicing and optimization across NVIDIA, AMD, and Intel. And the outcome section specifies a patented GPU-independent time-sharing GPU slicer that enables increased utilization and multi-workspace cluster sharing.
It's brilliant.
I want to spend some time here because this is where the economics of AI are fundamentally rewritten.
What's fascinating here is that it is arguably the most critical software innovation in the entire suite. To understand why, you have to look at the utilization problem in AI development.
Right, because not every task a developer does requires the full computational theory of a massive GPU.
Exactly.
Like if I'm a data scientist, I might spend 3 hours just cleaning my data set, writing basic Python functions, and running tiny test batches to make sure my code compiles. If I have an entire H100 GPU allocated exclusively to me during those 3 hours, that chip is sitting there at maybe 2% utilization.
Which is an astronomical waste of capital.
It's terrible.
But traditionally, sharing that GPU was fraught with peril. GPUs were architected to execute massive, parallel mathematical operations for a single overarching task. If you allowed 2 different developers to run entirely separate code bases on the exact same GPU simultaneously, their memory pointers would inevitably collide. Developer A's program would overwrite Developer B's data in the VRAM, causing catastrophic crashes for both of them.
So how does this patented time-sharing GPU slicer actually solve the physics of that collision? Like, I'm picturing a high-end commercial kitchen. The GPU is this massive, incredibly expensive industrial oven.
Okay, I like this.
In the old days, you had to rent the entire oven to one baker, even if they were just baking a single cupcake. It was horribly inefficient.
That is a brilliant analogy. What SDX and its GPU slicer do is introduce an incredibly disciplined expediter into that kitchen.
Oh, nice.
The software intercepts the compute requests from multiple different developer workspaces. It doesn't just throw them all into the oven at once. It utilizes advanced virtual GPU or vGPU techniques to physically partition the VRAM on the chip.
Like putting up walls in the oven.
Exactly, creating hardware-level walls between the workloads so they cannot corrupt each other.
Okay, so developer A gets partition 1, developer B gets partition 2. The memory is safe. But what about the actual processing cores?
That's where the time sharing comes in.
Right.
The software expediter rapidly microslices the processing time of the cores.
Microslices.
Yes, it gives the full power of the GPU cores to developer A for a fraction of a millisecond to execute a batch of math, then instantly flushes the context and hands the cores to developer B for the next microsecond.
Wow.
It happens so incredibly fast that from the perspective of the developer sitting at their laptop, their Jupyter notebook feels flawlessly responsive. They feel like they have a dedicated GPU.
But from the NeoCloud provider's perspective, they have just squeezed 3 or 4 paying customers onto a single piece of silicon without any perceived performance degradation for those lighter workloads.
Yep.
They have essentially quadrupled their revenue per chip for development tiers. That is the ultimate efficiency hack.
It is, and crucially, the datasheet explicitly notes this works across NVIDIA, AMD, and Intel architectures.
Well, that's huge.
That hardware agnosticism is a massive strategic play. It prevents the neo-cloud provider from becoming completely vendor-locked to a single silicon manufacturer's proprietary slicing software.
It gives the cloud provider leverage, right? Like, if AMD suddenly releases a more cost-effective chip, the provider can rack them, and SDX will seamlessly slice them using the exact same developer interface.
Exactly. The developer never even needs to know the underlying silicon changed.
It guarantees performance assurance and operational flexibility, which are absolutely paramount when you're spending billions on infrastructure.
Billions, yes.
Well, speaking of billions in infrastructure,
Yeah.
to truly comprehend how this technology impacts the real world, we have to examine the business mechanics of how it is actually sold.
The fun stuff.
Right. The final page of this datasheet is entirely dedicated to licensing tables and SKUs. It's just a wall of item numbers.
Yeah.
But when you map these SKUs against the architecture we just discussed, some fascinating philosophical patterns emerge about the future of enterprise software.
Yes, this raises an important question, actually, because the procurement mechanics often reveal the underlying strategy of a company far more clearly than their marketing copy ever does.
Definitely. Let's break down the divide here. The suite is sold in two fundamentally different ways. First, we have the higher-level tools SDX, the developer console, and SCD, the multi-tenant cloud director.
Right.
These are sold strictly as subscriptions. You buy a 1-, 3-, or 5-year license per node, and the support for these is tiered, standard 9 to 5 or gold 247.
Typical SaaS model.
Exactly. But then you look at the foundational tools, SAC, the Automation Center, and SCC, the Liquid Cooling and Power Manager. The core licenses for these lower-level tools are listed as perpetual.
Yep, perpetual.
So why this distinct split? Why operate a hybrid SaaS and perpetual licensing model within the exact same software suite?
It's a reflection of the physical lifecycle of the AI factory versus the innovation lifecycle of the software. Let's look at SAC and SCC. These tools are inextricably bound to the physical reality of the hardware. They manage the baseboard firmware, the bare metal OS provisioning, the power distribution, the liquid cooling loops.
The physical stuff.
Right. When a neo-cloud provider deploys a massive rack of servers, that exact physical configuration is going to remain in place until the hardware becomes obsolete and is physically decommissioned, which is usually a 4 to 5 year life cycle.
So it makes total sense to tie the software license to the capital expenditure of the hardware itself. You buy the rack, you buy the perpetual software license to manage the cooling of that specific rack, and they basically live and die together as a single CapEx line item.
Precisely. You don't want a subscription for the thermostat of a machine that isn't changing. But SCD and SDX, the multi-tenant network routing and the Kubernetes developer environments, those exist at the application and user experience layers.
Which change constantly.
Exactly. The features required at those layers are evolving at breakneck speed. The tools a data scientist needs today might be completely different in 8 months. So a subscription model, an OpEx expenditure, allows Supermicro to continuously push massive feature updates, integrate new AI frameworks, and adapt to the shifting cloud market, treating those top layers as an evolving service rather than a static piece of infrastructure.
It perfectly aligns the pricing strategy with the pace of innovation required at each layer of the stack.
It's very intentional.
But there is another distinction buried in the support tables for SuperCloud Composer, the cooling manager, that I found even more revealing about the power dynamics of the industry.
Oh, I know what you're going to say.
Yeah. Under the SEC section, there are entirely separate SKUs based on the underlying hardware management standard. They offer licenses for SEC running on a Supermicro-defined BMC standard, and a completely separate set of SKUs for an open BMC shared by a vendor standard.
The BMC, the baseboard management controller, this is where the real political battles of data center architecture are fought.
Right. For those who might not deal with hardware procurement at this level, let's explain the BMC. It is effectively a tiny, highly privileged, independent computer physically soldered onto the motherboard of the main server.
Basically a spy computer?
Sort of, yeah.
Oh,
It runs its own independent network connection and its own power. Even if the main server's CPU is completely crashed or the machine is powered off, the BMC stays awake.
Always on.
It allows the infrastructure team to remotely log in at the hardware level, check thermal sensors, update the BIOS, and force a physical reboot. It's the absolute lowest level of system management.
It is the ultimate backdoor to the system. And historically, hardware vendors, whether that's Supermicro, Dell, or HPE, invested massively in developing their own highly proprietary closed-source BMC software platform.
Right, because it was the ultimate walled garden strategy. If you force a massive enterprise to train their entire IT staff on your proprietary management interface and integrate all their automation scripts into your proprietary BMC API,
the switching costs become impossibly high.
it's exactly. When it's time to upgrade the hardware 3 years later, they are practically forced to buy your servers again just to avoid rewriting all their automation.
Exactly. It was a strategy of total lock-in. But the hyperscalers, the massive tech giants, and the largest neoclouds who are buying hundreds of thousands of servers, they absolutely despise walled gardens.
They won't tolerate it.
No, they refuse to be locked into a single vendor's ecosystem. They want the leverage to buy servers from Supermicro, Dell, and bespoke ODMs simultaneously and manage them all through a single, unified, vendor-agnostic toolset.
And that's where OpenBMC enters the picture. It's a Linux Foundation project originally pushed hard by companies like Facebook and Microsoft, right?
Yes.
To create a completely open source, standardized operating system for baseboard management controllers.
So when we look at these SKUs, we are seeing the physical manifestation of a massive industry compromise.
How so? What does this all mean?
Well, Supermicro is attempting to service two completely different philosophies simultaneously. By offering the Supermicro-defined SKUs, they are appealing to the traditional enterprise customer who wants a fully integrated, tightly supported, out-of-the-box solution where the vendor handles all the complexity.
Just make it work.
Right. But by offering and explicitly supporting the OpenBMC SKUs, they are bowing to the immense purchasing power of the hyperscalers.
They have to.
They do. They are saying, we acknowledge that you demand an open-source, heterogeneous fleet. We won't fight you on the BMC layer. You can flash our boards with OpenBMC, and our SuperCloud Composer software will still natively interface with it to manage the liquid cooling and power distribution.
That is fascinating.
Yeah.
It is a stark acknowledgement that in the modern AI era, the customers, specifically the hyperscale customer, dictates the infrastructure standards, not the hardware vendor.
Exactly.
The moat is no longer in locking down the baseboard management. The moat is in providing the higher level orchestration, managing the fluid dynamics, the multi-tenancy, and the GPU slicing, regardless of the underlying open source standards the customer chooses to adopt.
It is absolutely incredible how much a simple list of part numbers on the back page of a datasheet can reveal about the tectonic shifts happening in data center philosophy.
It really is. I mean, we started this deep dive looking at 4 dense pages of technical marketing, and we have essentially traced the entire life cycle and economic reality of an AI request, from the developer's fingertips down to the microfluctuations of chilled water flowing over the processors.
It is a remarkable unified stack of technology. It perfectly illustrates the hidden complexity of our modern digital lives.
Okay, let's do a quick synthesis of the journey we've just mapped out today.
Let's do it.
We started with cold, inert pieces of incredibly heavy metal. The SuperCloud Automation Center, SCEC, breathes life into them. It securely authenticates, automates the bare metal provisioning, aligns the heterogeneous firmware, and rigorously benchmarks the silicon, eliminating thousands of hours of manual, error-prone toil.
Right. And then, as those machines power up, ingest data, and begin generating staggering, rack-melting heat, SuperCloud Composer, SCC, takes control of the physical environment.
The thermodynamics.
Exactly. It ingests millions of telemetry points to monitor the power distribution and orchestrate the liquid cooling loops across tens of thousands of hosts, dynamically preventing catastrophic thermal events in milliseconds.
And with the physical plant running safely and efficiently, SuperCloud Director, SCD, steps in as the isolation layer. It carves up that massive raw resource pool into secure, highly performant multi-tenant environments.
It orchestrates the complex InfiniBand topologies.
Yes, and generates the cryptographic audit trails required to bring highly regulated enterprise capital into the AI space.
And finally, sitting at the very peak of the stack, the SuperCloud Developer Console, SDX, abstracts all of that underlying complexity away.
For the humans.
For the humans. It provides the data scientist with a frictionless self-service Kubernetes workspace, utilizing patented hardware-agnostic GPU slicing to squeeze every last drop of economic efficiency out of the silicon.
It really is a symphony of automated orchestration. So, to you, the listener, the next time you open an app on your phone and you use a seamless AI tool to draft a complex email, or generate a hyper-realistic image, or summarize a massive document in 2 seconds. I want you to pause just for a second.
Discard the illusion of the weightless cloud.
Exactly. Discard that illusion. Picture what is actually happening behind the curtain. Picture the massive, deafening, liquid-cooled, multi-tenant AI factories making that computation possible. Picture the invisible software layer, silently monitoring thousands of cooling lines for micropressure drops, dynamically slicing GPU milliseconds across dozens of workspaces, and managing an orchestrated chaos that borders on the miraculous, all so you can get your answer instantly.
Which leaves us with a highly provocative final thought, one that challenges the prevailing narrative of the AI boom.
What's that?
Well, in the tech press and on Wall Street, the conversation is almost exclusively focused on the race to build faster AI chips.
Yeah, it's all about the chips.
The silicon gets all the glory, all the investment, and all the headlines. But based on our deconstruction of this architecture, the real bottleneck for the future of artificial intelligence and the true defensible competitive advantage for these neoclouds isn't just the silicon itself.
Hardware eventually commoditizes.
Exactly. Hardware commoditizes. The real moat is the plumbing. It's the secure multi-tenancy, the thermodynamic orchestration, and the algorithmic slicing of those resources.
So the victor in the AI wars might not be the company that simply builds the fastest, hottest engine. It might very well be the company that best orchestrates the factory around it, the one who brings frictionless order to the heavy, hot, chaotic reality behind the magic.
It's a sobering reality check for anyone assuming that just throwing raw capital at GPUs is a guaranteed path to dominance in this space.
Absolutely. The abstraction is the product, but the orchestration is the business. Well, that is all the time we have for today's exploration. Until next time, keep digging into the details.